Alright, welcome back guys. We want to use Castigliano's theorem to find the deflection at point A here on this cantilever beam. And point A is at the location of an applied load, and this is great for us using Castigliano's theorem. This beam here has three different loads applied to it. It's got a point load, a distributed load, and a applied moment. So if we were to use the regular old virtual work method, that wouldn't work because that only is for times where we have one single point load on a structure. But because we've got a bunch of stuff going on here, we're going to use Castigliano's theorem. So the way that we write Castigliano's theorem, the deflection at the point that we're interested in this case we're looking at point A, is the partial derivative of the total strain, elastic strain energy with respect to that point, the point load that's acting at that location. So in general terms, you'd see like Yj is equal to the partial derivative of the energy with respect to Pj. So, but if we know the point, like it's at point A, we just write in the subscript A. All right. So if the elastic strain energy is the integral of from 0 to L of m squared over EI dx, then the partial derivative of it with respect to Pa, what we do is we just write, instead of writing m squared, we just write the first m over EI. Then we're going to take the partial derivative of that second m, so times delta m over delta Pa. All right, and that whole thing with dx at the end. So now what we need to do is we need an expression for m, the internal moment, in terms of x as we move along the span. So if we take a virtual cut starting, if we start at the left-hand side at point A and take a virtual cut somewhere just in the region to the right, we know that we're going to have Pa pressing down. And then halfway along, we're going to have the resultant from the distributed load. So this is going to be Wx. Basically, if this distance here is x, then it's going to be acting at a distance of x over 2. And then we also know we have the applied moment here, ma. So to complete our free body diagram, we're going to draw on the internal shear, and we're going to draw on the bending moment, the internal bending moment, in their positive directions. Okay, so if we go and sum up the vertical forces, we're going to get basically V plus Pa plus Wx is all equal to 0. So we're going to find that really the internal shear is equal to negative Pa minus Wx, or really what it is, it's equal to Pa plus Wx going in the upwards direction. And really, the first part of this is going to form a force couple with Pa going down, and the second part of this is going to form a force couple with Wx going down. The force couple with Pa is going to have that distance there of x, and the force couple with Wx is going to have that distance of x over 2. So when we go to take the sum of moments, basically, about some point, let's say the point right here, then we're going to get the expression, the internal moment, which we have going this way right now, that's all going to be equal to 0. And these are all going in the same sense. They're all giving us a counterclockwise rotation, basically. So what we do is we just isolate for m, the internal moment, and we're going to bring all the stuff over to the other side. So we get negative Pax minus 1/2 Wx squared minus ma. And this here is our expression for the internal moment in terms of x, right? Because as x increases, all this stuff's increasing and our moment is changing. So what we want to do is, that is going to be what we plug in here for our moment. We also need to take the partial derivative of this. So we have delta m over delta Pa. We take the partial derivative with respect to the point load that we're checking the deflection at. And so when we take the partial derivative of this with respect to Pa, we basically set Pa as our variable and everything else to constants. So when we take the derivative of that, this goes to 0 because there's no P terms there, this goes to 0 because there's no P there, and this basically drops down to 1, and we're left with negative x. Alright, so now what we want to do is we just want to plug that stuff in. So we can bring out the 1 over EI if we want, because that's going to have to come out eventually, just to make our lives easier. So we have from 0 to L, the expression for m is negative Pax minus 1/2 Wx squared minus ma. And the expression for the partial derivative of m with respect to Pa is just negative x. and that's all with the dx at the end. Let's not forget that. Okay, so what we can do is we can distribute this in, so we get 1 over EI as the integral from 0 to L. This becomes negative PA x, actually, sorry, we're distributing a negative sign in there, so that negative is going to drop out. So this is PAX squared. Again, this negative distributes in, so this is plus 1/2 WX cubed plus MAX. All right, that's all dx. Okay, so now we can just basically perform the integration one term at a time. So we have this 1 over EI. This is going to be times. This becomes 1/3 x cubed, and we sub in that L because zeros. We're going to subtract out all zeros, so we get 1/3 PAX cubed plus this x goes to x4 times 1/4, and 1/4 times 1/2 is 1/8. So we have 1/8 times WX to the power of 4, and we're going to sub in L for all those x's, so we get L to the power of 4 plus MA, this goes 1/2 x squared, so we get 1/2 MA x squared, but we're substituting in L for that, so boom, L squared. All right, now let's plug in everything that we have. So we have EI, we have PA, we have W, L, and MA. And we can reduce this a little bit. And if you just do that final calculation in your calculator, you're going to get 0.00133 meters. And you can convert that to basically 1.33 millimeters. And that is the deflection. YA. So this value is positive because it is going in the direction of the applied load that we used in Castigliano's theorem. So that's good to know. But otherwise, we did find the answer. Now you can compare this too if you want, using method of superposition and maybe tables or something. You can find the deflection caused on a cantilever beam just due to the distributed load, just due to the point load, and just due to applied moment. Add them all up together, and you're going to see that you're going to get this exact same answer. So there you go, guys. That is an example on using Castigliano's theorem to find the deflection where we have a point load acting at that point.